Hi everyone, our 17th lecture, expectation maximization. Hopefully everything will come together in this lecture for you and for me as well, because the ideas that we've discussed in the logistic regression, the ideas that we've discussed in density estimation, the ideas that we've discussed in clustering, and plus some new ideas that we've touched last lecture about latent variable modeling, uh, all comes together in today's lecture. Well, despite of that, that's not going to be too diverse lecture. It's just all of these ideas and in just one package, expectation maximization. Should be easy, can't be easier. Let's try it. And what will we cover is the outline, of course. And okay, let me small pause. Not ideal, but possible. Okay, good. So do we even need EM for Gaussian mixture models? We've considered Gaussian mixture models already. We'll come back to them again today, and you will come back to them again in the homework. Gaussian mixture estimation, a hack we will consider, well, you will consider that is your homework exactly. We'll consider what we can do in this difficult case, and then the easy part, hopefully, maximum likelihood estimation via expectation maximization, and in the presence of latent variables. Okay, let's go. So do we even need EM for GMMs? So just to remind you, Gaussian mixture model. Here's how the likelihood looks like right here. Ta-da! It's just a sum of k components, how many mixtures in the mixture we have, and each of them is a Gaussian, has their own mean, its own mean, and its own covariance matrix, and those pi sub k are the prior probabilities or the probabilities of each of those Gaussians, but for the purposes of what we're doing here, because this likelihood is a probability distribution, has to sum to 1, those pi sub k's, they okay, they also some unfortunate inconvenience, but that's fine. They also need to sum to 1. I don't know if I say it somewhere. Probably not. Oh, but you remember. And for simplicity, simplicity in this episode, in this subchapter, um, let's assume that we just have a diagonal covariance matrix, and not only it is diagonal, um, so identity times some values of variance. It's spherical because each component of the covariance is has the same variance, um, and it is spherical and the same for each of the Gaussian. So all we're doing is placing our Gaussian balls in just different places in space, but they're exactly the same in terms of their volume. Yeah. Then the probability of x, given that the class is k, is what I said, normal distribution or Gaussian with a specific mean, and they all have the same covariance matrix, diagonal covariance matrix, and it is also spherical. And probability, prior probability or marginal probability of getting a variable from this class is pi sub k. Mu's, the means of those distributions are parameters. And yeah, the rest, as I just already said. So, but do we even need hidden variables? Do we even need to do what we've done with k-means, right? First estimate hidden variables and then estimate the, uh, the what did we do? First we estimated the means, then we estimated the membership. So first estimate the means and then estimate the class posteriors, I guess. Okay, well, we'll see that in more detail. I don't want to get into that just yet at this slide. So, well, let's just write this down. So we have hidden variables because if we knew which class we're sampling from, we would just like if we knew those probabilities, then it would have been slightly easier, I guess, but not too much. And we have unknown means and unknown sigma in the general case. But the problem with this maximum likelihood estimation, comes from the following. We can just like say, okay, what do we have? Let's call it log likelihood. Ta-da, perfect. Let's differentiate our log likelihood with respect to pi and set it to 0. Let's differentiate with respect to mu's and set it to 0. Let's differentiate it with respect to sigmas and set it to 0. Solve this all together and be uh, done and happy. Let me check my next slide. Yes, yes, but uh, this would be difficult to optimize. So remember the exponential family that we've considered in one of the lectures. So probability distribution belongs to exponential family if it can be described or cast in this uh, shape, in this form, that you have some function of x, some function of eta, and e is your exponent, power eta transpose of some other function of x. And uh, one of those g of n is normalization factor, so that guarantees that probability distribution sums to 1. But when we're dealing with a probability distribution from the exponential family and compute maximum likelihood, remember we start for all of the maximum likelihood, we start with the IID assumption, so probability of x given some parameters, but then we're saying to simplify our lives and get rid of this product, we're taking a log of it, and which we we end up with log of p x theta. Great. When we're taking a log of probability distribution from the exponential family, and sum is over all of the data points that we've just collected, then we conveniently get this expression without any exponent involving x. This is usually easy to deal with, or easier. This doesn't involve x at all. This doesn't involve the parameters eta at all. So we factored out parameters from the data and all in those two um, factors, and we get rid of the exponent and usually have a nice form. Now, if we look at the sum of distributions from the exponential family And obviously Gaussian is from the exponential family. So if we look at the sum there, sum of exponential family distributions is not in the exponential family. Furthermore, for example, for Gaussian, the sum of Gaussians, weighted sum of Gaussians, is a universal function approximator. We can approximate any function um, in the like with the sum of Gaussians, or to say it in different words, we can expand any function in the basis of Gaussians. So when we write our log likelihood of Gaussian mixture model, or a Gaussian mixture, what we get is this expression that is hard to deal with because we have sum under the log, and if we want to differentiate and then we want to set to 0 and optimize, this expression has multiple uh, will have multiple components and will be the best to optimize. Uh, so people usually try to avoid that. Sometimes maybe there are special cases when it will work and will be okay, but most generally it's a difficult optimization problem. So another problem, but this problem is common to the maximum likelihood, but it's worth mentioning here. So suppose we have two components in the Gaussian mixture, and suppose by chance, either at one of the assignment problems, because one point was an outlier and the mean was closer to it, or just imagine any other possible way this could happen. But suppose one mean just by chance coincides with one of the data points. So what's going to happen with our maximum likelihood estimator? So here's the Gaussian, just for simplicity, just one Gaussian. So when the mean and the x are like when they're equal, this is going to be 0, and e power 0 will be 1, and that's what we're going to end up with as our probability density. Um, not not the probability density, but the probability at this point, right? So let's just split this expression that we just saw, the otherwise just normalization constant, but now because x and mu are equal, we get this. And when we try to maximize the likelihood of this expression of Gaussian, one of the mixture components, for which by chance the mean fell right on a data point, like it's easy to maximize. Just push our sigma to 0, and the closer to 0 you get, the larger your likelihood becomes, and that means an explosion, right? We have an explosion here that we get a delta function that goes to infinity, and the whole process, if we're doing it numerically, just blows up. Or even if we don't do it numerically, it it's just problematic. But no, nothing else will happen. It's like a local local minima, or local maxima, since we're maximizing our local maximum, since we're maximizing our likelihood. But the problem there is that it's not only a bad local maximum, but it's also um, like a singularity point where everything diverges, or well, explodes. Okay, that will be our next section.